If I differentiate x cubed, 3x squared over 3 factorial. What's going to happen with the 3? I'm going to be left with 1 over 2 factorial. Differentiate this. 5x to the power 4 over 5 factorial. What's 5 over 5 factorial? 1 over 4 factorial. Let's differentiate this. Minus 7x to the 6 over 7 factorial. What's 7 over 7 factorial? 1 over 6 factorial. That's another easy one. Or you can just come in and differentiate here. What's the derivative of x to the power 2n plus 1? X to the power 2n plus 1 minus 1. We all know calculus 1, right? X to the power 2n plus 1 minus 1 is x to the power 2n. Multiplied by 2n plus 1. You all know your calculus 1. And what's 2n plus 1 over 2n plus 1 factorial? 1 over 2n factorial. The question is, can I do that? The answer is not all the time. You can't just differentiate one series to obtain another series. The question has to do with, does this converge? Does this in infinity converge to this? Does this in the infinity converge to this? The answer, not always. So we have some series here. For example, when does this converge to this? Now, if you look at this one here, the geometric series, what's the common ratio? 1 plus x squared plus x squared. Huh?
Common ratio is x.
And it will only converge if the common ratio
Less than 1.
less than 1 in absolute value. This will never be the same as this one, x is 1. This will never be the same as this one, x is 1. I'm going to convert when x is 1. Certainly not going to converge when x is 1.1. Because when x is 1.1, you're going to get 1 plus 1.1 plus 1.1 squared plus 1.1 cubed plus 1.1 is going to go big. And when x is 1.1, this is negative 10. That's it. When x is 1.1, this is negative 10. And this is infinite. So this is only valid for certain values of x. Values of x that are close to 0. Let us say up to negative 1 and up to plus 1. Same here. If x is 1.1, this is 1/10. But if x is 1.1, this is growing big. So we need to talk about the convergence on these things. So we need to know when do these converge? And we know how to deal with those things. We have the ratio test, the comparison test, alternating series test, all that stuff. All that stuff. When this converges to this, then you may differentiate this. And how would you differentiate this? Well, you differentiate that, differentiate that, differentiate that, differentiate that. All of them. And add them up. Right? Yeah. If you have this series here, and we say that it's 1 plus x squared plus x cubed plus x squared. The coefficients are all 1. If you differentiate this, what do you get? Oh, by the way, how did we obtain the series first? You had to do this now. You all remember it. Plug in 0, differentiate. Differentiate again, plug in 0, get A2. Plug in 0, differentiate, get A3. Plug in 0, differentiate. I'll take a look at your notes from last time. That's the hard way to do it. You can also see that if you differentiate this, what will you get?
1 over 1 minus x squared.
1 over 1 minus x squared. And if you differentiate this, what do you get? Then you have the series for this. Nice trick. Nice trick. So you don't have to do this. That's fine. You say to yourself, hey, you know what? You want the series for this being the derivative of this. So the series for this should be the derivative of the series for this. Perfectly acceptable provided this converges. But this will only converge for x between 1 and minus 1. What is the derivative of x to the power n? And x to the n minus 1. If you know your calculus 1. And there it is. got Taylor series for this. Well, the long way would be to do this one. And do what? Plug in 0 on both sides. Differentiate, 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 plug in 0 on both sides, and to sift out those coefficients. That's a nice exam question. What is E0? What is E1? What is E2? That's the hard way to do it. Anybody know what's the easy way to do it? Yes?
Could you take the integral of that 1 over 1 minus x?
Correct. What is the integral of 1 over 1 minus x dx?
Ln of 1 minus x plus c.
Mr. Bredau says the integral is ln 1 minus x plus c. Who agrees with Mr. Bredau? Put your hand down.